Next, of course, we have to look at the net work problems. Okay, so what we have is a little equation relating the speed before and after for an object that is being worked upon. Okay, so let's take a little car right here and work on it. If we exert a force on this over a certain distance, we will cause it to change its speed from whatever it was to some number, some new number. Okay. In this particular problem, let's go ahead and define some things. Force is 500, mass is 100, initial speed is 0, so it's starting from rest, and distance is 50 meters. So what we do then is basically just put all the things where they belong and solve for whatever we need. What I want to find in this particular problem is how fast is it going when it reaches its end distance, okay? So basically it's going to be worked on by this force for 500 newtons for 50 meters, and then they're going to stop caring about it. Okay, so what is the final speed at that point? So how we do that is we go ahead and plug in stuff into our equation. Now, we have a force and we have a distance, and we got to remember what work is. Work equals force times distance times an angle usually, but these are going the same direction, so that's fine. So what we'll do is we'll have work equals 500 times 50 meters, okay? And it's a very simple calculation. I almost hesitate to put it inside of the field of view because I'm sure that you can do this in your head. 500 times 50 is 25 grand. So the amount of work that we have done is 25,000 joules of work, Newton meters of work. Okay, so then what we can do is we can set that work equal to the change in kinetic energy. So let's go ahead and do that. Work. Dang it. I didn't need to rewrite that. Get out of here. 25,000 is our work. Equals 1/2 times our mass of 100 kilograms in this case, times the final speed squared. And you might be wondering, oh man, he doesn't have any room. Well, sort of. We got to remember what the initial speed is. Mass times 0 squared. Right? He did run out of room, but what is 0 squared? 0. What's 0 times anything? 0. So this whole term goes away. So we can just rewrite this to 25,000 joules equals 1/2 times 100. I'll just rewrite it. Might as well. Kilograms times VF squared. Now, we just do some simple math at this point. We take 1/2 times 100. 25,000 joules is equal to 50 kilograms times VF squared. Okay, divide both sides by 50. Okay, the math portion, the simpler part. Always it is the problem that you have the setup, right? The setup is the problem. Also, I'm not Russian, I promise. I'm not a Russian spy. Now, oh look, there's the reflection of my hand. Now, we could put this into our calculator, 25,000 divided by 50, but if you are an astute observer, you'll remember that 500 times 50 is 25,000, so the answer is going to be 500. So 500 equals, and this is going to be meters squared per second squared, due to the units canceling, equals VF squared. Take the square root of both sides, dink, and you get a final speed of 22.36 meters per second. So if you exert 500 newtons of force, just about the gravitational force on a regular old kid, over a distance of 50 meters, about 150 feet-ish, okay, you would end up pushing that person to a speed of 22.36 meters per second, which is getting on the realm of about 50-ish miles an hour. Okay, so if you exactly, 50.31, nice, good job, me. Now, this is how you find how fast you're going at the end of a work problem. What you can do from there is you can then apply this setup, this problem-solving tactic, to find the initial speed of something that is going to be moving at the bottom of a ramp. Okay? So you can apply this speed that you just found to a new setup. Okay? So like we did in this previous problem, we had an initial speed up the ramp of 20. Well, let's say that the initial speed up the ramp was 22.36. That would be the work equaling the change in the energy here, okay? The conservation of energy, which is kind of nice. You can put these two types of problems together, shove their ideas together, and it'll work. It'll work just fine.